All right. It's a pleasure to welcome today's Tao seminar speaker, Markus Ammann, hailing from Switzerland, Paul Scherrer Institute, nearby Zurich in the Aargau, Canton Aargau. I was lucky to convince him to stop by SoMAS. Of course, he has to stop by SoMAS before heading to a Simons Foundation meeting this afternoon in Manhattan. So I'm glad he could make it. A few short introductory words. He is a true Swiss-bred scientist, did his diploma masters at the ETH Zurich, the Swiss Federal Institute of Technology, in physical chemistry on photoemissions and solid-state physics. Then followed up with his PhD also at the Swiss Federal Institute of Technology. So we are both alumni in that regard. Also working on photoemissions and on volcanic gases and ashes, how they interact with radiation. Did a postdoc in the University of Bern, the capital of Switzerland. I've never been in that university. I don't know the place. But then pretty readily became a staff scientist at the Paul Scherrer Institute. And just within a year, you became group leader of the surface or multi-phase chemistry group. Multi-phase meaning looking between aerosol particles and gases or interfaces in general. And the environment is full of interfaces, obviously. He was visiting scientist in Irvine, California, University of California, is now an adjunct professor at the ETH Zurich. And I think what is really remarkable, and the community is very grateful for his services, he is member of the, you may not know, International Union of the Pure and Applied Chemistry, IUPAC. And what does that mean? That means these are the folks who evaluate all reaction rate, kinetics, constants. So if you use a reaction rate gas phase, aqueous phase, multi-phase, heterogeneous, he is one of the evaluator looking at thousands of papers and giving proof of, it's a valid rate you can use in your model. So they make the final word, and they did that for decades. I saw the IUPAC exist since 1870 to make sure the chemists use the right rates and not just a faulty, by accident, a faulty paper or something. And so he did tremendous work in that regard. And it's in all our models in principle, that input. Without further ado, so today Markus will talk on the impact of iron on chemical evolution of atmospheric aerosol particles. Welcome.
Okay, thank you. Thank you, Daniel, for the kind introduction, and welcome to my presentation here. It's a pleasure to be here. I know Daniel since quite a while, and it's always nice to come here for spending some time. I also apologize that I slightly adapted the title from transition metals to iron to not be too broad, and also I don't have so much to say about other transition metals than iron. And then I also, since at the end usually there is no time left for acknowledgements and of different people involved, so I just list here the current members of my group involved in these activities, PhD students and postdocs, then the list of the previous ones that are mostly contributing to the results I'm showing, because the current ones have not yet got that far.
I'm sorry, someone says they don't hear you on the, let me see, what is our audio? Well, the mic is on. Yeah. Should be all good, or so I can hear. Okay, great. Just continue. Sorry about this.
No problem. And I think I can take this mouse. I'll start with this. No, not very fun. And then we collaborate with a number of groups at both at ETH in Zurich, then also with Max Planck Institute of Chemistry in Mainz, with the group of Thomas Berkemeyer. Then we do some aqueous phase box modeling with the group of Hartmut Hermann at Troppers in Leipzig. We have some collaboration on some aspects of this with Alan Bertram at the UBC in Vancouver. Then some activities with Markus Ammann at the University of Basel, with UC Boulder and the Rhino Volcanoes Group, with EPFL, Satoshi Takahama for some FTIR measurements. Then also we had an experiment with Andy All's group in Michigan coming over for some smoke chamber experiments. Funding is mostly by Swiss National Science Foundation, which is kind of the equivalent of the US NSF here, and some European program funding. Okay, so with that, I have to.
Big page down. Or
Yeah. Okay, good. So Paul Scherrer Institute, so just that you know a little bit where we are. So we are 30 kilometers northwest of Zurich, between Zurich and Basel. So this is the Aare River, which takes most of the water from the western part of the Swiss Alps and carries it further down to the Rhine River. So the German water to Germany, and the Rhine River is just a few kilometers downstream. And so this is the PSI campus. So we are about 2,500 people, which is a little bit smaller than BNL, but just everything crunched together on a much smaller area. And originally this was an institute related on the left, on the east side of the river, this was the Institute of Nuclear Engineering in the 60s, founded in the 60s. On the right side, this was more the physicists, machinery with accelerators and particle physics. And then 30 years ago, they merged everything to become the Paul Scherrer Institute. And now we are very broad in energy, health, and biology, medicine, and condensed matter physics, really very broad. And the main unifying theme and also task of PSI is to develop and operate large research facilities. So we have neutron source, we have a synchrotron, you see it over there. We have proton accelerators, and also some kind of energy-related plant systems. And so it's really, really broad, right? And I'm coming from the Laboratory of Atmospheric Chemistry. As Daniel mentioned, we are now called the Multi-Phase Chemistry Group, and this is the picture of the group members from 2024. This is also reflecting more or less the contributors to the work I'm showing today. And we are part of the Laboratory of Atmospheric Chemistry, and we are within the PSI Center for Energy and Environmental Science. So just that you see roughly the embedding that we have. So, I mean, usually, or maybe, yeah, how should I start, right? So we have, I mean, some of you are atmospheric chemists, some of you are more maybe on the ocean side of things. So in atmospheric chemistry, kind of the bulk of the atmospheric chemistry is a lot of gas phase chemistry, where a lot of the emissions interact with each other, react, and get oxidized. We have interactions with forming aerosol or interacting with aerosol. We have ice particles, we have clouds in the troposphere, and all of these interactions at this level here, but also when it comes to interactions with the oceans, this creates a lot of interfaces and interactions among the different compartments. And this is why the atmosphere can really be considered a multi-phase system. In our group, we also have kind of a little bit a spread between more molecular level processes. So we have quite some activities, kind of surface science activities, which are really tackling kind of the top 1 or 2 nanometers with the spectroscopy. We do some imaging also of particles, and I will show examples today. And this is also something that links me to Daniel here. We do photochemical processing, including stuff with iron that I focused on today, but also then in interaction with different other species like halogens or nitrogen species. And then another process level theme is that we worry about diffusion in exchange with the gas phase, and the fact that the condensed phase is not only liquid water, but sometimes very highly viscous phases. So these limitations imposed by diffusion are very important aspects of our work. So just very briefly, I think I don't need to tell too much about the biogeochemistry of iron, because I'm sure there is quite some activities going on here, but just a little bit as an introduction, where is iron coming from? And of course, most of the people first think of mineral dust from deserts and arid areas, and that is certainly a very important contribution, but there's also a lot of, and this is the topic of this review by Ito et al., is that there is a lot of pyrogenic iron from combustion processes, but it's not only combustion processes, but also other anthropogenic sources. For instance, railways are generating quite a lot of emissions of iron-containing particles. On one hand, from the railway tracks. So in German, we say Eisenbahn, the iron line, in a way, right? So we say it even in the language. And then also the brake pads from both railways, but also of cars and trucks, generate iron, and also other transition metal containing particles. In the atmosphere, we have a lot of aging, and this also serves a little bit also as an introduction to these processes in aerosol particles. So we have these emissions, and then in the atmosphere, we have oxidation of other gas phase species, and the products of this, the oxidized organics or sulfate or HNO3, ammonia, they all may interact with these iron-containing dust particles. They lead to further processing. So, for instance, if we have mineral dust and we condense nitric acid on it, then of course some of the iron may be dissolved out of the mineral, the original mineral, and this then is of course important when things are deposited to the ocean as a nutrient to the ocean as well, right? So, and indeed, when you go and look, you find iron everywhere. So these are concentrations that you find in surface area, micrograms per cubic meter. And I mean, and as I have said, because the sources are really widespread and everywhere, you can also find it in most places at significant mass concentrations. And of course, you see a little bit some of the sources directly reflected, but you see more in the context of arid areas. So here, for instance, the outflow of from Sahara, North Africa, over to the Atlantic, and many other examples here on this map apparent as well. So very often, iron and carboxylic acids are associated in ambient aerosol particles, and I will come back to the role of carboxylic acid and iron in a minute, but just, and this is also something that I'm not sure whether Daniel was involved in this Moffat et al. Paper, but that was before or after?
Yeah, before.
Before it was. And essentially, so using scanning transmission X-ray microscopy, so they found that in several field campaigns that roughly 5% of all the particles contain iron in the air, and once you can detect them with Dixon, you know that roughly about 5 to 8%. So more than 5. So usually 5% of the particle contain iron to more than 5 to 8%, right? Which is already a significant amount, because as I will show later, iron has a catalytic activity, right? So you don't need a lot of iron to have a big effect. Then also, as I mentioned, we often find correlations between carboxylic acid, for instance, the oxalate, with the water-soluble iron amounts. And also, so here I was involved as well in the measurement. So we found a lot of different carboxylic acids to some degree correlated also with the dissolved iron in. So this was from a campaign in northern Italy, in the Po Valley. So why are these carboxylic acids important? Carboxylic acids, especially especially tricarboxylic acid, but also bicarboxylic, dicarboxylic acid, they form very stable complexes with iron. And all these, or the majority of these complexes, absorb light in the UVA range very strongly. And when you absorb light in the UVA of an iron 3 complex, so you transfer an electron from the carboxylate ion to the metal center. You reduce the ion that way to ion 2, and the complex falls apart, and you oxidize the ligand. So this means that photolysis of the iron 3 complexes is one of the bigger sinks of carboxylic acids in the atmosphere overall. So these are model results from Hartmut Hermann's group using the so-called Capra model, which is a fairly explicit H-phase chemical mechanism. And what you see on these plots, and there will be another one on the next slide, so I'll try to explain it. So the box has a certain amount of aerosol particles with a certain composition, depending on the scenario they're using. And then this air parcel is lifted, and then the particles form cloud droplets. Chemistry continues, then the cloud evaporates again there, and what is left remains with the aerosol, and then it continues to interact chemically with the gas phase, and then may form a cloud again, and so on. And what you see here now are the different sinks for carboxylic acid, for a selection of carboxylic acids as a function of time in the cloud, in the dry aerosol, and again in cloud. And so what we see here that during the cloud phase, so the one of the bigger sinks for carboxylic acids for this one specifically at this point is the complex, the ion complex photolysis, often exceeding, for instance, reactions with OH in the gas phase. So this is really exceeding reaction with OH in the condensate. So photolysis of ion carboxylates is very important. And also, it's not only the ion carboxylate complexes that photolyze, but also ion hydroxide, for instance, is a very important OH source. So now this is an inverted plot. Now what's plotted are the OH source strengths. And now we see that during the particle phase, we have a large source from the reaction of H2O2 with ion 2. So this is the Fenton reaction, generating during the aerosol phase, generating the vast majority of OH, only a small contribution from the direct photolysis. And this has also to do that in comparison, for instance, to the iron carboxylate, the absorption spectrum of iron hydroxide is shifted more towards the blue than iron carboxylate. So they absorb really in the UVA. But very important here, the Fenton, this is the so-called Fenton reaction, producing OH. That's strange, it doesn't show up here. What is that? No? Yeah, I'm sorry for that. So the product here is OH1. So this is the strongest OH source in the particle phase, in a particle that contains iron, of course. And it depends on the scenarios that we use here to calculate that. So now what are the consequences? And I'm just, before I go into, I'm going to explain a little bit the context of our own experiments. Just one example here, apart from carboxylic acid sink, or an OH source, which has, of course, a whole lot of other consequences. So this is a results from China, where they looked into how much of the chlorine that is produced in this area is attributed to iron 3. And whatever the process is in details, it could be via OH radical production, but it could also be other more direct effects on how you generate the chlorine atom. I already had a little discussion with Paul this morning about what is probably the true oxidation process in here. But just as an example for the implications of the presence of iron in aerosol particles, among other things, production of chlorine, and now I'm probably I don't want to lean too much out of the balcony, and I was not aware that you were involved here in this work, right? And so in this work, Van Herpen et al., they found that the chlorine activation that you get from the interaction between mineral dust emitted from the Sahara and over the Atlantic Ocean, when it mixes with sea salt aerosol. So once you get internal mixture with sea salt aerosol, chlorine can be activated, and this chlorine then, upon photolysis, producing chlorine atoms. These chlorine atoms are then an important sink for methane. And people are now even thinking of solving our climate problems by mitigate methane by actually injecting a lot more iron-containing aerosol in the atmosphere to oxidize methane more efficiently. Another aspect of iron-containing aerosol, they are really health relevant. So as you probably know, is that nowadays when you think of the 5 most important life-threatening things that we are exposed to, particulate matter is among those 5 most important risks for reduction of our life expectancy. And this comes from a large number of epidemiological studies. So just the air we inhale is one of our biggest risks, along with, I don't know, smoking, I think, what is it? Dietary, and number 4. Yeah, I don't
Drinking?
Huh?
Alcohol,
yes, right. Yeah, thank you. So this is really very important. And one of the things that people believe is due to overloading our antioxidant system in the lungs by generating reactive oxygen species. And as I just mentioned, this phantom chemistry with iron is generating reactive oxygen species also in our lungs when we inhale them. So apart from other oxidants that we may inhale, for instance, peroxide in secondary organic material, but also the iron, once it can interact with the antioxidants in the lung, we have some reactive oxygen species producing cycles in the epithelium layer in the lungs, which can then probably perpetuate some of the health impacts that we experience from particulate matter. So iron is also important in that aspect. So now coming a little bit more to the details. So I will talk mostly about aqueous aerosol, and especially about aqueous aerosol containing organics. And one of the important issues with these aqueous organic aerosol is that they are very viscous. And under many conditions in the atmosphere, when relative humidity is maybe not close to 100, but maybe like 60% or so on average, and especially also when the temperatures are getting lower, then the conditions are such that we often approach the so-called glass transition temperature. This is the temperature at which we expect a particle to form a glass, right? And whenever this scale bar is 1 or above, our particles are more like glass marbles than liquid droplets. And we see that once we go on the surface to high altitudes where it is colder, we have these glass marbles. But even at 850 hectopascal, we already see a lot of red. Or also here in the temperate zones, we may get very viscous particles. And this is important because this slows down chemistry, because we slow diffusion because of this. And so equilibration timescales may get very, very long. Right? So the particles may get out of equilibrium to some degree. Then another aspect, I will talk about photochemistry. I already have mentioned why, because these ion complexes absorb light. And now I see, this is when you open a presentation on another computer. Somehow the color scale has messed up, not on this screen, but only on this one. That's funny.
Blame it on the projector.
Okay, so then it's projector, doesn't matter. So if we have solid or liquid particles, so when we have an interaction with gas phase species, so for instance OH radicals, so the OH radicals will hit the surface, and any chemical reaction will most likely occur on the surface. If we have a liquid particle, the OH radical, maybe is a bad example, still also probably reacts very close to the surface because it is so reactive, but ozone, for instance, will diffuse throughout the particle. When you look at photochemical processes, even in this case, the photochemical, at least the first generation photochemical radicals and intermediates will be formed throughout the particles. So this is really photochemistry. As long as the particle is transparent and you don't have attenuation of light, the radicals are generated throughout the volume of the particle. So this is very important for photochemical processing of the particles. And then there is also quite a number of different feedbacks between photochemistry and viscosity. And so these things have often been studied in the context of biomass burning aerosol or brown carbon, as the name says. Brown carbon means it absorbs light quite a bit. And of course, let's say if you generate an excited species of aromatic carbonyl, for instance, then of course viscosity is important because it tells you how easily it is to find a partner for energy transfer or for electron transfer and things like that. So there is a direct impact of viscosity on the way photochemical processes work out. But then also once we have photochemical processing going on, the viscosity may change because we change the species, the speciation of the aerosol particle, and then maybe they get more viscous. This is results from Alan Bertrand's group, where they showed that photochemically processed secondary organic aerosol is much more viscous than the original aerosol was at the beginning. So now a little bit to the detail of what we did with iron-containing aerosol. So as I mentioned before, when we start with an iron 3 carboxylate complex, we may have this ligand to metal charge transfer with reduction of the ion, so reforming iron 2. Iron 2 is reoxidized with oxygen, with HO2 radicals, or with hydrogen peroxide to reform the iron 3. The iron 3 will find another carboxylic acid, forms a new carboxylate species, which can undergo photolysis again, right? And this is what I mentioned before. So this is catalytic in the ion. So it's a photocatalytic cycle here, also referred to as Fenton chemistry. And then when we have the ligand oxidation, very often it undergoes decarboxylation, depending a little bit on the structure of the molecule, and this bit of CO2, which we can detect in the gas phase. Once we have this carbon-centered radical here, the most likely fate of a carbon-centered radical in the environment is reaction with oxygen. forming peroxy radical chemistry, and then you go to many generations of peroxy radical chemistry that ultimately oxidize this system, right? We have continuous feeding of new carbon-centered radical. We have oxygen, and then we go through all these multi-generational oxidation processes. And now we have looked at different things. We have on one hand looked a little bit into how copper interacts and interferes with this iron 2 and 3 cycling. We have looked at how this chemistry interacts with nitrate ions that are in there, and it can demonstrate that we form a lot of reduction products from nitrate, which is not direct nitrate photodissociation, but indirect photochemical reduction of nitrate. We also see conversion of NO2 to HONO, which is not, as we originally thought, reaction with HO2, but it must be another process that reduces NO2 to HONO, which we have still not completely figured out what it is. And then we have also looked into interactions with the halide ions, and one particular case that I will briefly address is the reduction of iodate to form I2 and maybe also HOI as products, so a recycling of iodine species. So, and I will now go to some of these examples. How am I doing with time? So I didn't.
15 minutes.
15 minutes left. Okay. So we work with iron citrate, and iron citrate is a very stable complex, and we use citrate or citric acid, the free acid, because this is resembling pretty well typical secondary organic material. So it's a hydroxy acid with we have 3 carboxyl groups and an alcohol group. So this is a very reasonably well representing secondary organic aerosol. Upon photolysis, you generate a particle complex, and then it frees up this kind of very short-lived species that will decarboxylate and generate this carbon-centered radical plus CO2, and the carbon-centered radical then forms first a peroxy radical, which is very short-lived and
Is it too late to add something?
under oxidation of the
Is that an apple?
So this is
Can
first
I take
generation
it? I'll take it.
ketodiacids that we can also detect. So the colored ones are the
I
things
know,
that
I saw that, but
you
then
look at the
I'm
ion
very picky
oxidation
with
state,
wine. Sometimes it's too strong.
you look at formation of some of the products. So the first technique that we are using is hanging transmission X-ray microscopy, and we use that to determine with spatial resolution the oxidation state of iron. And so
maybe there's another one over here.
This works. We have a zone plate to focus an X-ray beam to a very small spot of 20 nanometers or 25 nanometers in the plane of the sample. And so here we have our particles on a silicon nitride membrane, and then there is a detector on the other side which collects the image. And then we raster the sample in front of this focus beam. And so this is a standard technique nowadays, and many synchrotrons. And what the special thing that we have developed at PSI is this kind of sandwich cell. So we have 2 silicon nitride membranes and not just one, and we have a housing through which we can pass gases. So we can expose these particles to relative humidity, also to ozone if we want, and whatever is needed for a chemical reaction. And then the additional feature here is that we can replace the detector in a very short time with a UV LED and irradiate the particles and then switch back to measure them. So we cannot do it in parallel, but we can irradiate them and then analyze them in the microscope. So we can look into, we can photolyze them, and then look at the evolution afterwards. And so what we then learn from this, so we are using essentially the method generates or brings us an X-ray absorption spectrum for each pixel in an image. And this allows us to differentiate iron 2 and iron 3 and determine the fraction of iron 3 with pretty high spatial resolution. And so what you see here is that when maybe I should use the mouse and not walk here because those online will not see. So what we see here after irradiation with light, we see that most of the particle, somehow now I'm missing the color bar, somehow this has gone lost.
Yes, please.
I'm sorry for that. So the darker the color is, the more it is iron 2, and the lighter the color is, it is iron 3. So we see here after 7 minutes after photolysis, we only see just a little bit brighter color at the surface. And then after 15 minutes, not much change. And then only after, in this particular case, after more or less almost 2 hours, we see a substantial reoxidation. And this reoxidation is due to the peroxides that are in the particles after photolysis and also due to oxygen entering the particles. And the surprise was, and this was really the story here, and this was work by Peter Albert, who worked with me after he left Stony Brook, I think, not immediately, he first went to Lyon and then to my group. And so what we learned from this is that I explained to you that after photolysis, we generate a carbon-centered radical, which requires oxygen to generate peroxy radical. But of course, oxygen is not terribly soluble in such an aqueous system. So out here now, we have roughly about 10 to the minus 4 mole only of oxygen in an aqueous system. And this then, of course, limits the ability to form peroxy radicals. And what we found is that by tuning a little bit the process model to understand in more detail how the system works, we see really that the oxygen is a limiting reactant. And because as soon as we are at lower relative humidity, we notice that oxygen is depleted really from the right at the surface, and we don't have oxygen anymore in the bulk of the particles. And this is relatively surprising. I mean, we are in an oxidizing atmosphere, and photochemistry, even under realistic atmospheric conditions, generates so much radicals that oxygen is not enough to drive the peroxy radical chemistry.
Okay.
So the other experiment that we are doing, and so maybe now I have to speed up a little bit, we are doing so-called coated wall flow tube experiments where we take our iron citrate material, mix it with citric acid and coat it onto a glass tube. And then we irradiate this in the reactor with humidified air to control the humidity. And then we have a bunch of analysis tools at hand. So we use a CO2 analyzer to measure the CO2 from decarboxylation. We also have, so when we work with nitrogen oxides, we have a NOx analyzer. We have a cavity-enhanced DOA system, or we had a cavity-enhanced DOA system from Rainer Volkam's group from Boulder. So we used his cavity for I2 measurements. We have also contributed a bit to the development of a similar cavity-enhanced absorption spectroscopy system for a company in Heidelberg, originating from the University of Heidelberg, to detect nitrogen dioxide and HONO with 2 separate cavities. And then we also have a SIM system to look at products for some of the experiments. And then we also now, this is now in collaboration with the group of Thomas Berkemeyer at Max Planck Institute for Chemistry. We have this detailed layer resolving chemistry transport model, you would say, right? So simulate diffusion with pretty high depth resolution. And then we have the whole mechanism, which is very complex. It's about 50 or so reactions that we have implemented, including then diffusion for transport and especially for
What they
oxygen
use
from the
them for?
outside or species that move out
Yeah.
to the gas phase. And in here we have the process, photolysis process.
Here? But their house is inside. That's why I'm confused.
Reoxidation drive and reformation of the complex. And then
You go down and then you
this
go
is just
right.
one example. So
And then you
the
go
gray
right.
lines here are the observations of CO2 formation in such
Wait,
flow tube experiments. And the green shaded areas are the model output.
Because
After
you go
optimization to a big data set, so we have a complete
then you go
data
right,
set under many
and then you go
different
right.
conditions with
And that's how you get to the
variation of
point.
the ion contents, variation of humidity,
But you can walk.
oxygen, and things like that. Then you optimize that.
I
and
can
you
walk
see
to my
it's
friend's
not
house. They have a
perfectly,
car, and then we're
more or less
inside.
match as good as we can to constrain the chemical, the chemistry, and all the kinetic rate coefficients. And what we then see, we are not going too much to the detail about these different
I do want to
but
push it,
what we learn from
actually.
this
That
is
sounds
that
pretty good. It's
when we
different.
look at the degree of oxygen saturation under these
Send me the
photochemical
address,
conditions,
please.
then and this is a radial scale here. So we see that when we have particles which are maybe 1 micron in size, as soon as we are at, I don't know, maybe 60% or more, we have substantial reduction of the nitrogen saturation within the particle. And the average humidity in the atmosphere is, I think, about 60%. Right? And this is at room temperature. So at lower temperature, it would be even more pronounced. We also looked a little bit into the effect of copper. So copper was expected to be a net Hox source. So copper can react with both OH and with HO2. And through that would shut down. We would expect it would shut down part of this reoxidation chemistry, but it was entirely different, as always in science. The hypothesis was completely inverted. And in the end, copper actually accelerated the reoxidation. And we only had a hypothesis that it is because in relatively concentrated system, copper and iron can form the iron citrate can form polynuclear complexes. So they chain up with the oxygen ion in different citrate complexes. And through this change, there is diamagnetic coupling. This is known from solution measurements. And we think if you replace one of these ion centers with copper, that you can speed up the reoxidation. But it remained a hypothesis. To also bring this a little bit to more an atmospheric representative system, we also want to know now in reality when we have ion-containing aerosol emission. So what happens when we form secondary organic aerosol on these particles? So to study that, we designed some experiments in the PSI atmospheric simulation chamber. So we had ion-containing seed particles fed in the chamber, and then we oxidized terpenes. So this was alpha-pinene, and then looked at the products with mass spectrometry. So we used extractive electrospray mass spectrometry to have an as good as possible and complete as possible analysis of the particle phase. And I only really briefly summarize here. So when we had iron, we could form more SoMAS. And this is probably because the iron is leading to a higher sink for the larger molecular weight compounds, so more the dimers in the condensed phase. And also we noticed that there is some kind of inverted Fenton chemistry going on, because the peroxides that are contained in the particles from secondary organ oxidation of the VOC, the peroxides can also reduce iron 3 to iron 2. And so we have, even in the dark, we have some radical cycling going on without even the light being there. So this is quite an important aspect. And then, of course, maybe I directly switch here. Under light, when we switch on light, we really see a massive increase of aerosol mass. Of course, these particles now contain significant fractions of iron, and maybe a bit more than 5%, or like 10 to 20%. And under these conditions, we really lose SoMAS substantially within minutes. So this is really a massive sink for organics in the condensed phase, right? But this also tells us a little bit, yeah, if we don't put this in a model, I don't think that we can get our SOA right? So if 5% of all particles contain significant amounts of iron, then I think this will affect the lifetime of SOA. So this is not yet published. This comes up soon. Very briefly, I'm not really going into the whole breadth of iodine chemistry. Iodine is a very important halogen, not only for us, for human health. Iodine is emitted mostly from the ocean, and mostly through deposition of ozone, which reacts with iodide in seawater, and we release a number of different iodine species. And then in the gas phase, there is a kind of a bunch of reactions that cycle iodine species among different species in the gas phase, and most of them also partition to the aqueous phase. And in the aqueous phase, then in principle, it is well understood how you oxidize iodide through HOI, HIO2 into IO3. And in principle, if you believe the classical chemical mechanisms, all of the iodine would soon end up in iodate in its most oxidized form. However, because there is a significant fraction always remaining in the gas phase, there must be processes that reduce iodate to somewhere between iodate and I-, so that you can have recycling to the gas phase again. And this is then also the reason why some of the iodine survives the tropospheric oxidation processes and end up in the stratosphere, as demonstrated by Rainer Volkamp's group. And so we were interested whether our iron carboxylate photochemistry is indeed reducing iodate. And of course, I wouldn't show it here if it would not happen. So we indeed see strong and efficient reduction of iodate, and we see emission of IO2 coming. So we see here that the gray line is the CO2 from the carboxylation of the citrate ligand. And then a little bit shifted in time, we see the strong emission of I2. And we have done a number of experiments that it is quite non-linear in iron and in iodate contents. So we still do not fully grasp exactly the chemical mechanism. So we have looked into this, what's the name? This iodine cycling reactions that are known from chemistry classes. I can tell you now the name of this, of the mechanism. Doesn't matter. It's a very famous. If you Google for iodine oscillation reaction, so this is a system where you start with iodide and H2O2, and then you watch it over time. It turns black, transparent.
They use your fingerprint.
Yes. Yeah.
Is it the iodine clock?
Yes. Yeah. And so we put in that in the mechanism, but it does not fully explain what we observe. So there must be something else that we still don't understand. What is also interesting, so we hooked up the chemical ionization mass spectrometer, and so we see HOI, we see IO radicals, we see even iodine atoms being emitted, and of course the I2. So this I2 was measured with the cavity, and this was measured with the SIMS. But then also we see really a range of iodinated organics. So we even see triply iodinated organic species, not a very high concentration, but the fact that we see them indicates the vigorosity of chemical reactions going on in the system. And maybe the last thing I want to mention we also started to be interested in so-called redoxification. So as you have probably learned in atmospheric chemistry class, I hope Daniel is doing that.
Well,
So oxidation of the nitrogen oxides essentially brings the nitrogen oxides to HNO3, and HNO3 is either dry or wet deposited, and once it is there, you're done with nitrogen. But it is not entirely the case. So sometimes some of the HNO3 finds its way back to the gas phase, and people have, and then of course, if it is not lost, it feeds again, knocks into the gas phase oxidation side. And so there is a number of studies that have looked at the photolysis of particulate nitrate, and there has been a lot of debate and speculations about that. And the point is that photolysis of nitrate, or apparent photolysis of nitrate, leads to more NOx than what you expect from pure photodissociation of nitrate, assuming its absorption cross-section known from aqueous phase measurements. And the speculation is mostly that nitrate sits on the surface of particles, because people don't know anything else, so they believe it sits on the surface of the particle. It probably has a non-complete hydration shell, and due to that, more quickly photolyzes. And I don't believe that. And the interesting feature is that in most of the, for instance, evidence from field campaigns is that the less nitrate you have, the more efficient is this redoxification rate. And yeah, and this is still not understood, and we have ourselves started to tackle this by looking into, so this is now not iron, but simply using organic chromophores to see to what degree organic chromophores present in biomass burning aerosol would reduce nitrate. And we indeed find a correlation between the nitrate photoreduction or indirect nitrate reduction, photochemical reduction rate, and the fraction of water-soluble organics extracted from biomass burning aerosol. And we have also put that into model output from Geos Chem with the help of Colette Held, now at ETH in Zurich, to figure out how much honor we produce from this mechanism. So this would be the idea to do that also for iron carboxylate photochemistry, where we indeed see again, so this is a blank experiment without iron, so we measure some photodissociation of nitrate as expected. It's in the range of 10 to the minus 7 per second. So this is roughly, this is more than a day of lifetime photolysis. But once we have iron citrate complexes in there, we see this huge, at least an order of magnitude larger photoreduction of nitrate, right, which we believe is due to an indirect mechanism. We don't know yet, but what is really the reductant? It could be aqueous, so solvated electrons that are generated in this system. So we don't know that. We still have to do competitive competition kinetics experiments to scavenge electrons and see whether that affects this. Okay, so I think I should stop here. Maybe I leave the conclusions here and rather take some questions. Thank you.
Thank you, Ammann. Okay, few minutes for questions before we head to lunch. Thank you for this really nice overview talk. Any questions? There was a lot of topics. John.
I mean, if no one else.
No, go ahead.
Okay, I'll try to limit myself. But first of all, for your iron citrate photolysis experiments, where did the chlorine come from? And was it limiting in any way?
We did not do chlorine ourselves.
Okay, but you did FEC, you were.
Iodine.
No, you did FeCl2 from the iron citrate photolysis experiments. You showed the.
No, that was only a reference spectrum. That was only a reference spectrum that we took
to show the F2, Fe3, Fe2 ratio.
Yes.
Okay. So I guess my question though is that as you were going from Fe3 to Fe2,
yes,
how would that be impacted by the presence of chlorine? In other words, you're talking about a carboxylate or an acid complex.
Yeah, it depends on whether you have an ion. I'm not sure about the UV spectrum of ion chloride, right? I guess this is also a complex, and I assume. I mean, let's say if I put chloride in our system, most likely ion citrate will be the more stable complex than ion chloride, because ion citrate is just more stable than almost everything else. That's why we took it.
Gotcha.
But of course, in a real system where you may have less good ligands to iron 3, maybe then you also form ion chloride. And then I'm not sure what happens, right? I'm not sure whether that has been studied well enough. Because for ion citrate, there are complete detailed photophysical experiments that identify the transition state and everything, right? So there we really know there is a really good basis from the literature about the detailed chemical physics of the photodissociation process. For ion chloride, I don't know whether anybody has done that, right? So I have not yet worked with ion chloride myself. I would like to start that, right? Because it's a very important system. And because there is not so many other possibilities to activate chloride into chlorine. So if this works really well, right, then it's a pretty unique feature. But I could imagine that there is direct electron transfer. Why not directly chloride gives its electron to iron 3 to reduce it? But I'm not sure.
You got the ion mobility, right? So
yeah, of course, you need to have a contact.
That kind of leads to my next question. So the modelers like to use pH in the models, of course. How do you represent pH, and what does that really mean from an experimental perspective? You know, are you comfortable with working in the area and trying to figure out what your pH is?
Yeah, so these are all.
I'm talking like real world.
Yeah. So now in the citric acid ion citrate system, pH is around 2. In the SOA systems, which is then more realistic, right? It's about 4 in those chamber experiments. At least when using this kind of pH paper.
Thermodynamic stuff,
but not really measured on a pH paper. The method that also Alt is using, and he calibrated it with Raman. So in principle, I don't know how reliable it is, but it is a bit less acidic than the ion citrate citric acid system. And in the coated wall flow tube experiments, we also do pH dependent experiments. So there we can vary. Right? And so we try to understand a little bit what the effect of pH is on the chemistry. So yes, but I mean, in reality, usually aerosol is acidic, which means that the dissolved ion, whatever the source is, remains dissolved, right? And because as soon as you go to too high pH, you precipitate some hydroxides and whatever, right? So and then you are done with some of the photochemistry of the homogeneous phase photochemistry. But even if you have ion oxides as a multi-phase system in the liquid phase, like solid ion oxides, you still have photocatalytic activity, because ion oxides are usually they have a band gap, and you can have photocatalysis also with the solid semiconductor results. So I'm even not sure whether you really shut it off, but that would be interesting to simply dissolve goethite into an aqueous solution and put in chloride, and then whether you see chlorine from that as well.
All right, that was a deep dive. Anyone else question, or everyone is hungry all the time? Oh, come on, Sima, you have the last.
I have a very basic question. When you are introducing the problem, you had a map for the sources of iron.
Yeah.
And I looked at the distribution between the US and Canada. That was a huge, very fast.
Clear difference. Oh yeah.
What happened to Canada? They don't drive. There are no railway cars.
No, I think maybe there is not enough arid areas in the upwind, right? I mean when you look here, what you get here in North America all comes from North Africa, right?
Right.
And up here, I don't know, we don't have so many deserts here
Force latitude.
in the middle northern latitudes, right? And then there is nothing to be transported over there. I guess it's mostly that. So maybe we don't have enough railways in Switzerland to bring too much of iron to Canada. So just because there is not enough, I think. I mean, there is.
But there's also dust coming from China coming across the Pacific. So
Yeah,
that
I mean, it is not nothing here, right? So it's still blue. It is still blue in Canada. It's not white. So it still has
Yeah, it's hard to see.
10 nanograms per cubic feet. So it's not zero.
All right, let's leave it like that and heading for lunch in the Swenson rooms. Thank you, Markus, for the
Thank you.
great overview.